So, just to remind you, we do have our problem session in room 5. For some reason, I had a senior moment last week and thought we had to be in room 190. We're in room 5, okay? Okay, so we're talking about rotations and tensors in quantum mechanics. So what we discussed last time was that there are these two different groups that play a role when we're talking about rotations. Okay? The group of rotations in R3, that is three-dimensional Cartesian space, the group that generates rotations is the group SO3. That is the group of 3 by 3 orthogonal matrices with unit determinant. Okay? And that group is a Lie group. It has a Lie algebra. And that Lie algebra represents the local rotations, local to the identity. And it is an arbitrary element of the algebra is a linear combination of basis elements. And that basis of the Lie algebra is given here, either in terms of, we can write them in terms of real antisymmetric matrices, or we could factor out an I if we like. And that the algebra then is defined by this Lie bracket. Okay, so this is the group SO3. And that group tells us how rank K tensors transform under a rotation. So if I have a tensor and that's a prime, you can't sort of see because it's next to the arrow, but this is the rotated tensor. Its components are related to the original components through these rotation matrices. Okay? In contrast, the group of rotations on Hilbert space, and what I mean by rotations, these are again supposed to be what I'm going to mean by rotations. It's not an arbitrary rotation in the sense of a vector in Hilbert space or vector's vector. It's the one that's generating the equivalent of the geometric rotation of a 3D space. And that group is the group SU2. And SU2 is the group of, or its defining representation, is the group of 2 by 2 unitary matrices with unit determinant. Okay? And its Lie algebra is the group of 2 by 2 traceless Hermitian matrices. Okay? Now, if you look at those matrices are the Pallies, and if we put an over 2 over them, then they're the angular momentum operators in quantum mechanics. That's where we got the group of SU2 by thinking about what physically a rotation is. It's what's generated by, that's what we define as angular momentum. That's not quite right. Now it's right. This Lie algebra is the same as this Lie algebra. So the groups SU2 and SO3 have the same Lie algebra. What that means is that locally they look the same, but globally they're different. It's like the difference between a sphere and a donut. Okay? Locally, they're both two-dimensional manifolds that are flat. And you could look at it, if you're an ant on the donut, you wouldn't know that you're not in flat land. But if you walk around, all of a sudden, you get back to where you were. If you go through the hole, and you can shrink yourself back to the right You know, it's simply connected or not simply connected. So that's kind of what a little bit of the difference is. We're not going to go into the details about that. So SU2 and SO3 are very closely related groups, but they're not the same group. Okay? And what is true is that SU2 is a double covering of SO3. So I can map the two elements in SU2 to the same element in SO3, and if I do that for every two elements, then I get the right group structure. All right? Now, as we've discussed, there is a defining representation of these groups as a group of matrices of a certain dimension, 2 by 2 matrices or 3 by 3 matrices. But we can have different representations of the group in terms of matrices of different sizes. As long as the composition law is right, it is a representation of the group. Okay? And so what is the case is that we can write down an arbitrary dimension matrix representation of the group SU2 as the matrix representations of the rotation operator in quantum mechanics for an arbitrary J. When J is a half, this was the defining representation. But when J is 1, this is a representation in terms of 3 by 3 matrices. When J is 3 halves, this is a representation in terms of 4 by 4 matrices, 5 by 5 matrices, etc., etc., etc. So those are all representations, different representations of the group SU2 in terms of different dimensional matrices. And these are all irreducible representations. You cannot further block diagonalize this. Okay? And this is written here in terms of the standard basis, the eigenstates of J squared and Jm. Okay? Now, you should kind of note that when this J is an integer, then in this case, rotation by 2 pi is the same as not rotating at all. That's still the identity. But it's still a representation of SU2 because it still respects the group structure. All right, now one thing I forgot to mention last time I want to pick up on here before we get to talking more about tensor products and such is, let me get a better chart. How do we find, so what if I want to have some kind of, what's the word I'm looking for? A formal expression. I want to actually write down what these matrix elements are. Okay, right now I wrote them down, but it is a formal expression, but it's not an easy one to use. Okay, so one of the ways we do that is through the Euler angle construction. So, do you remember the Euler angles? You guys ever do that in classical mechanics? Let me remind you. So what is the construction? Well, if you think about what a rotation is in three-dimensional space, it's a mapping of a Cartesian basis to a rotated Cartesian basis. If I know how to do that, that defines the rotation. Any map maps a basis to a basis. So I can think about it in you know how I am on ground perspective, I'll do my best. So here we are. Here is some original basis. Okay, this is some Cartesian basis. Now I want to go to a new Cartesian basis. Now, what defines, how do I define that Cartesian basis? Well, one thing I can say is that there's a new z-axis. Okay? That new z-axis is some direction in space. And it's defined by some angles here, right? There are two angles that define where the new z-axis is. But that doesn't completely define what the new three-dimensional basis is, because I have to ask how I could rotate the x and y coordinates. This is x prime and y prime. You get the gist. That is perpendicular to z prime, but I can have it arbitrarily oriented, right? So there's another angle. So there are three angles that define what this new basis is. Now, the three angles I showed you there are not actually the way the Euler angles are defined, but you see that there are three angles that define this, okay? And so I can define an arbitrary rotation as a rotation by three angles, alpha, beta, and gamma. Okay, and so this is a different parameterization of a rotation. Here I parameterize the rotation by an axis and an angle, right? The axis is defined by two parameters, the angle is a third parameter. You need three parameters. It's a three-dimensional Lie group, okay? So these are called the Euler angles, and they're defined in the following way. I first rotate around the z-axis by angle gamma. I then rotate around the y-axis by the angle beta, and then I rotate again around the old z-axis by alpha. There exists, you know, if you do the geometry, for every reorientation of the basis, there exists a set of alpha, beta, and gamma that do that, right? You see that? It's not obvious. You have to play around with the geometry, and I'm not going to try to draw it. I'll let you think about it. Why is this a useful parameterization? It's a useful parameterization because it, in some sense, reduces everything. Well, before I say that, let me just back up and say one other thing. Pardon me. Rotations around x and y and z don't commute with one another, right? And the reason, so what this says, I can generate a rotation around an arbitrary axis by just rotating in sequence around y and z without ever rotating around x. I could do that because y and z rotations then generate something that looks like also a rotation around x, right? Because they don't commute. So that's why this works. If they commuted, well, then it wouldn't work. All right, so the reason we like this parameterization in quantum mechanics is that, remember, this is a rotation around the z-axis. And in the basis of the standard basis, so let's look at this. For a given j, okay, this is what we would call the rep for that j, m prime, given alpha, beta, and gamma. Okay, so that's a matrix. These are the matrix elements of that rotation operator in the standard basis for a fixed value of j. Well, look what that is. That is are eigenstates of JZ. So what is the action of a rotation operator around the z-axis acting on that? It's a phase, right? Because dz about theta is e to the minus I theta jz, right? That's what that means, right? And so when I act this on this, this gets replaced by the eigenvalue m, or m prime in this case, right? So this is e to the minus I gamma times m prime. It's an eigenvector, is that clear? And this is an eigenvector of this. It's the conjugate, e to the plus I alpha m. So this is equal to e to the I alpha m minus gamma m prime times j m d y beta j m prime. So what we have now reduced this to says any irrep dj and m prime for three is parameterized by three Euler angles. And all I need is this one matrix, and everything else follows. I just need what the matrix representation is for rotations around the y-axis, and then I can fill in the other parts by just multiplying with the phase. And these things are called the Wigner D matrices. You know, Eugene Wigner, the star of our show this semester, has really worked all this stuff out. Oh! Thank you. I thought there was a suicide. Sorry, bad joke. Anyway, I don't know if you heard this horrible story about the plane that looks like it was a pilot flew it on purpose. Sorry. Back to physics. So these are the Wigner D matrices, and you know they're calculated, and you can just look them up, or you can do your homework and do it yourself. Okay. So that's that. All right. So this is so then we have an arbitrary way of writing down rotations. All right. So continuing on, what we were talking about at the end of the lecture, what we want to pick up with now is the question of tensor products, spaces, Hilbert space. What we had discussed last lecture, and let me just quickly review that and follow up on that, is we considered the case of two spin 1/2 particles. And if we're looking at the spin degrees of freedom, then we said that the Hilbert space of that system could be written as the tensor product of the Hilbert spaces associated with each spin 1/2 particle. Each of these is a two-dimensional Hilbert space. Of course, we can also write that Hilbert space as a direct sum as opposed to a direct product, which is to say we have two subspaces rather than two subsystems corresponding to the total angular momentum, okay, of 0 and 1. So in this case, we have J1 is a half. We have J2 is a half. And this is the total J, which can be either 0 or 1 by the rules of the addition of angular momentum, right? So what we discussed at the end of the last lecture is we said, let us consider an example where we had, say, a rotation around the y-axis by pi. Okay? So, in that case, what we said is, well, for a given spin 1/2 particle, the rotation matrix around the y-axis by pi was 1 minus 1, 1. Right? That's e to the minus I pi sigma y. Okay? That's what we showed last time. That's for a given. So a rep of this rotation on the total Hilbert space H we could write as a tensor product of those two matrices. One acting on the first spin and the other acting on the second spin. Okay? We could assert that is certainly a rotation on the Hilbert space by that, right? And that matrix was that one, right? That's just the tensor product of this 2 by 2 matrix with itself. So this 4 by 4 matrix is in the basis up, up, the tensor product of the two bases, up, down, down, up, and down, down. Right? So if I take an arbitrary vector in the Hilbert space and I write it as some superposition of these states, then this matrix applied to it gives us the rotated state. Right? Now, as we showed, and let's review that, this is not a reducible, this is not irreducible. This is a reducible representation. There is a change of basis that we can do that will block diagonalize that. If we could do that, then this representation is reducible. Okay? So, what we did is we said, let's look at the basis, the coupled basis. The basis 1 over root 2 up, down, plus down, up, down, down, and up, down, minus down, up. Okay, that's another basis. It is, of course, the basis of triplet and singlet, which is the basis of total angular momentum, j equals 1 and j equals 0. Right? So, we see here, if I look at this rotation operator, so this is D on the total Hilbert space, acting on, say, the state up. Let's look at what that does. Okay. Well, what does it do? It takes it to down, down. Right? That's what this matrix does. This matrix takes the symmetric combination with total spin projection 0 to what? So that would be the, in this thing, it would be 1 over root 2. Right? And I act that on the matrix. And what does it give me? Minus it, right? So it's minus that state. Okay? And similarly, if I apply this matrix to the anti-symmetric case, what do I get? It'll be this, if this is, I mean, one of these guys is plus, and that takes what this guy's minus, that, so it's minus itself again. And finally, dy by pi on down, down goes to up, up. So, this rotation operator, or rotation matrix now represented in the coupled basis, what does the matrix look like? So now let me just write it as an ordered basis with singlet up here. And then the three triplet states, up, up, 1 over root 2, up, down, plus, down, up, and down, down. So this matrix takes this back to itself with does nothing, right? This guy takes this state to this state. This guy goes back to itself with a -1. And this guy goes to this guy. Right? So this matrix is block diagonal. And it's block diagonal where it's a direct sum of a one-dimensional representation for j equals 0 on direct sum with a three-dimensional representation for j equals 1. This is a 1-by-1 block. And this is a 3-by-3 block. See, did you have a question about you?
I'm sorry.
Yeah.
I'm wondering, so when d of y acts on the state,
Yep.
is it better to think about it as, is it changing the state, or changing the basis, or are those equivalent and it doesn't matter?
So this, as we've always described, this is an operator on the state.
Okay.
And it changes the state onto another state.
Okay.
So I could look at its action on basis vectors, right?
Yeah.
But these are always what we call active
Okay.
rotations rather than passive.
So so physically, I mean, you
You're
could
changing this state into that state.
Okay, cool.
That's what it does. Yeah. All right, so what we have here is this kind of way we see that if I have different ways of representing a matrix representation of that rotation. I have, here is one representation, it's a representation in this basis, and it's a reducible representation. This is another representation of the operator. We've known this from almost day one in quantum mechanics. We can look at different matrix representations of the same operator. The thing that's new here is this notion of reducible and irreducible with respect to groups. Okay? And what we see here is sort of a general kind of rule that I would say we would write in the following sense. If I have, consider the space H, which is, say, the tensor product of two Hilbert spaces associated with two angular momenta J1 and J2. Okay, this is, we looked at this where this was a half and a half, but let me talk about this more generally. Of course, this Hilbert space is also, can be expressed as a direct sum of Hilbert spaces associated with the total angular momentum J. Because I can break up I mean, in this Hilbert space, I think about the natural basis here. Is the tensor product basis where M1 goes from minus J1 to plus J1. It's a 2J plus 1 dimensional Hilbert space. This M2 goes from minus J2 to plus J2. It's a 2J2 plus 1 Hilbert space. So the dimension here is 2J plus 1 times 2J 2 plus 1. Here we have 4 by 4 because this was 2 times 2. And J ranges from what?
That's the value of J1 minus J2 plus J1 plus J2.
Thank you very much. Right. So, and for different J's. And of course, this, the dimension here is the sum over all those J's to J plus 1. And it's your job to check when we add this up. It's the same Hilbert space. This dimension, of course, is the same as that dimension. Okay? So what this tells me is that if I have two irreps, an irrep on J1 tensored into an irrep on J2, together this is not an irrep, but a direct sum of irreps. That's what we just did. We had a 2 by 2 irrep, a 2 by 2 irrep. We tensored them in, and that was a direct sum of a one-dimensional irrep and a three-dimensional irrep, corresponding to the total angular momentum spin 0 or spin 1. Now let me just quickly come back over here. Are these the matrices we would have expected? Just think, what is this? This guy is e to the minus I pi j, where j is 0. What is the representation of the matrix the matrix representation of the operator jy in the singlet subspace. It's the identity matrix, right? Because J is 0, right? So no matter what, this is the identity. So that is the phase, e to the minus I pi times the identity, which is minus 1 times the 1 by 1 identity. Yay! Smiley face, the guy with the little hair. Okay? So that worked. What about this guy? Well, this is just the Wigner D matrix for beta's pi. Okay? The Wigner D matrix is a rotation around the y-axis. And that's why I chose the y-axis, so I can write it down. So you look it up, and you find, I gotta go back and look it up. Here it is. That d1 of beta is equal to 1 plus cos beta over 2 minus sine beta over root 2, 1 minus cos beta over 2 sine beta over root 2 cos beta minus sine beta over root 2, 1 minus cos beta over 2 sine beta over root 2, 1 plus cos beta over 2, whatever. It is what it is. Okay? And you plug in beta equals pi. 0, 0, minus 1. 1. Yes. 0, minus 1, 0. Yes. 1 minus 1, 1, 0, 0. Yes. Okay, so it works. Okay, so how do we generally see this relationship? Well, let's go back. What we see here is this is the relationship between the coupled and uncoupled bases. Okay. This is also sometimes known as the irreducible versus reducible basis. Okay, that's sometimes how people will describe these things for this very reason. Let us review this. We've talked about it before, but I want to get a little bit more into the guts that we haven't previously discussed. So what do we have? What this says, there are two bases. So the reducible basis, this is the tensor product of the two bases. Okay? These are the simultaneous eigenvectors of J1 squared, J1z, J2 squared, and J2z. Right? We have the coupled basis, which we write as a total angular momentum quantum numbers J and M, and also the individual magnitudes. So this basis are the simultaneous eigenstates of J squared, Jz, J1 squared, and J2 squared. where of course we're writing j here as j1 plus j2, which is a shorthand for j1 tensor the identity on 2 plus the identity on 1 tensor in 2. This is just a shorthand for that, right? Right, so these are both bases. So what we have is the following. Let us fix J1 and J2. Okay, so we're looking at a subspace of the total Hilbert space with a fixed value of J1 and J2. Okay? This is a complete basis. If I sum this, M1 goes from minus J1 to plus J1, M2 goes from minus J2 to plus J2, right? This is the identity on this Hilbert space. But it is also, the coupled basis is also a good basis. And so I can sum over all values of J and M, and that's a good complete set. It also sums the identity. And I can change from one representation to the other, right? So the change of Hilbert space basis is defined by the unitary that goes from one to another. And those matrix elements are defined by this inner product. And these things are known as the Clebsch-Gordan coefficient. And it's Gordan. Now, there is a plethora of notations associated with the Clebsch-Gordan coefficients. Okay? They're all over the map. And it's confusing how you denote them. But this is our convention. I'll call them the CB coefficients. So firstly, since J1 and J2 are fixed, there's no need to write it on both sides of that. So I'll define my CG coefficient like this. This is my convention, and it's a convention that's a very standard convention, but not universally used. Okay? These are the things you have to specify to specify the Clebsch-Gordan. You have to specify the two J's, the total J, the two M's, and the total M. That's what you have to specify. Okay? Now, what can we say about these coefficients? Well, firstly, I claim that this coefficient, if I sum it over the M1 and M2 values, that this sums to 1. How do you prove that? Any thoughts?
certain identity.
Yeah, exactly. So there's the identity. I can take the inner product of this, say with a given capital J, capital M on both sides. That's the after value squared of that. That inner product is 1. I get that expression. Right? Or alternatively, if I sum over all J and M, according to the sum that I just wrote of these guys, it's also equal to 1. Right? By the same argument. I can take the sum, this sum, over capital J and capital M, and take the inner product with one of the uncoupled bases, and that will square to 1, and that's the identity on this side. So that's one thing we see about these Clebsch-Gordan coefficients. Of course, we know that there are what we call the selection rules. That this CG coefficient vanishes unless, firstly, it must be the case that the total projection M is the sum of the individual projections along the z-axis. How do you prove that? Thoughts? What is M? What does it mean?
It's the eigenvalue of the...
JZ, the total JZ, right? So I have JZ, of course, is the sum of the JZs on the two spins, right? So I can put this operator in, act it to the left, I get the eigenvalue M, or if I act it to the right, I get the sum of the M's. So they have to be equal. The other thing we have is the triangle inequality, which that is J. This is harder to prove, but can be proven. So that's the selection rules. There are other properties of the Clebsch-Gordan coefficients that are provable, but we won't go through them. In days of yore, one had to dig up Clebsch-Gordan coefficients in the particle data book, little pamphlet I had in graduate school, or there's ways to get at these equations first, at these coefficients using recursion relations, using the fact that, for example, J plus and minus is the sum of J plus and minus for each of these guys, right? And then you apply, you had to do this for homework, it was nasty. You apply the J plus on the left, you do it on the right, God, forget it. You just go on the internet or use Mathematica and just get them, okay? So what can I tell you about the Clebsch-Gordan coefficients that, okay? So, number one, we can choose by convention that the CG coefficients are real. They're not complex amplitudes. We could have made them complex, but we can choose one of them to be real and all the others follow from the recursion relations. Okay, so they're real coefficients. They can be positive or negative though. And then there's, where is it? Here we are. The symmetry properties. Symmetry properties tell me that Jm, J1, M1, J2, M2 is equal to the following. Suppose I change M1 to minus M1, M2 to minus M2. Well, then this is minus M, but with a sign up front. And that sign is J1 plus J2 minus J. I can also switch, suppose I switch which one comes first. It's a non-zero guy. Suppose I put J2, M2, semicolon, J1, M1. That would still be a non-vanishing guy. It would be the same, but with its different sign. And that sign is the same J1 plus J2 minus J. Jm, J2, M2, semicolon, J1, M1. So if I flip which one comes first, there's a sign difference. Or I can do this. Let me explain this in a moment. So this is a different thing where I take this and I subtract this amount of angular momentum. That is, I get this angular momentum left. As long as J1 and J2 add to this total J, that's a non-vanishing coefficient. It satisfies these guys. But it's related through these degeneracy factors. You can prove it, you can't, so it is what it is. Okay? And they go there like that. Now, I should say one last thing, which is sometimes, because of the fact that these guys aren't, in some sense, have a nice property with respect to exchanging the different J1, J2, and J's, there's another way to express these things. Instead of the Clebsch-Gordan coefficients, you will sometimes see what is known as the Wigner 3J symbol. Okay? So the Wigner 3J symbol is denoted J1, M1, J2, M2, J3, M3. This kind of array, and it's defined to be the following. Minus 1 to the J1 minus J2 minus M3 divided by the square root of 2J3 plus 1, the Clebsch-Gordan coefficient, J3 with minus M3, J1, M1, J2, M2. The thing about the Wigner 3J symbol is that this is symmetric with respect to cyclic permutation of columns. So I can commute any of the columns and it's the same thing. These phase conventions take care of that. So sometimes people like to use the Wigner 3J symbols, but they're not naturally a change of basis the way the Clebsch-Gordan coefficients are, so I don't like them. But you'll see them. All right.
I have a question.
Yes, please.
For the third symmetric property where you have like -1 to J1 minus M2, is there a formula for bringing out, like, so the bra is J2 minus N2, like could you switch it around?
Sure. I mean, you could, and you know, these are, you combine these different properties together, you get other properties. So absolutely. All right, let's continue then. So let's, based on these properties, what we see is we can write explicitly now how we go from the tensor product of representations to the sum of the irreducible representations. Okay, so let's consider the tensor product between two arrays. Okay, so I can take this and I can write it in the uncoupled basis, or the reducible basis. This guy by definition, that's the product of these two matrices. Tensor product of these two matrices. I guess I should have primed on these guys. Right? And that is equal to N1 prime tensor J2 N2 prime. Now, of course, what I can do is I can insert the identity. And change basis. I can insert the identity in the form of the coupled representation. Right? And when I do that, what do I get?
Which of the J2 N2s have the dash on it?
This should have a dash.
Clebsch-Gordan coefficient.
I get Clebsch-Gordan coefficients, right? And on this side, what I get is the irreps in J. So this then is the sum over J1, M1, J2, M2, Jm. I have the Clebsch-Gordan coefficient Jm with J1, M1 prime, J2, M2 prime, D, J, M. This is known as the Clebsch-Gordan series. But you see what's happening here. I've written a tensor product of irreps as a sum of irreps, and this get weighted by the Clebsch-Gordan coefficients. So it's the form. Now, this expression is a kind of generic kind of thing that we see. And I want to talk about a few cases. So, suppose I do the change of basis. This is my basis vector as a tensor product of basis vectors. This itself can be written as this Clebsch-Gordan series. I don't really have to sum over n because there's a delta function here where m has to equal m1 plus m2. This is another example of a Clebsch-Gordan series. We start with a tensor product of two vectors, and I end up with this other guy weighted by Clebsch-Gordan coefficient. It has the same basic structure as this. It's one we're going to see again and again. Here's an example. Let's consider spherical harmonics.
One of those ends be N1.
It should. Thank you. Sorry. All right. What about a spherical harmonic? Well, I can relate my spherical harmonics to rotation matrices. How do I do that? Well, what do we mean by this? This is, of course, the wave function associated with the angular momentum ket. Right? So I can think about this is really theta and phi define a direction in space. Okay, so here's three-dimensional space, x, y, z. And here's right? So this is a function really of that direction in space. I can say YLM as a function of that direction in space is really the representation of the ket LM in position space. Of course, the position is the position on the sphere. Okay? So that's the wave function. Right? Now, this vector is just a rotated vector of the z-axis. So I can say that the ket n is a rotation, some rotation, on the position vector along the z-axis. So this is the position ket on the z-axis, distance 1 from the origin. What rotation is this? Well, I could say first I rotate around the y-axis by theta, and then I rotate around the z-axis by phi. Then I get this. So this is equal to a d around z by phi, d around y by theta. On z. Okay. This, of course, is equal to a set of Euler angles that are these. That's what we just had. Right? So, what this tells me is that YLM of theta and phi is equal to EZ d dagger alpha equals phi, beta equals 0, phi, theta, gamma equals 0, acting on YLM.
Why is it's complex calculus?
Because I took the adjoint to make it like that. Okay, I need to remind myself of something that, yeah, that's right. Okay, good. Right. Thanks. So, all right, so now let me say, so YL, YLM of theta and phi is equal to EZ. Now I'm going to insert a complete set for the fixed L, sum over M prime. L M prime, B alpha equals 5, beta equals theta, gamma equals 0. Why don't I have that sum over L? The reason is that the rotation matrix maintains the magnitude L. It only changes the direction N. Okay. What is this? Well, that is an irrep for that L, and that M prime M for alpha equal for all this stuff. And luckily, right next to us, we have what that is. So this is equal to, yeah, well, I'll just leave it as that. And then we have to ask, what is this thing? Well, that's a little bit of a mess, but it's not that hard to show that these things, of course, this is what I said earlier, written over here, was that the YLM along a certain direction is, or in space, is just the representation of this. So this is a YLM along the z-axis, which are the Legendre polynomials. This thing is the Legendre polynomial at equals 0, and it turns out that this thing is equal to the square root of 2L plus 1 over 4 pi, and it's only 2 times. So the bottom line of all this mess is the following. This is equal to the square root of 2L plus 1, YLN of is equal to square root of 2L plus 1 over 4 pi. This should have been dagger, huh? So this is star. Okay, what was the point of this exercise? Well, the point of this exercise comes back over here. This is going to start the basis of our discussion of the Wigner-Eckhart theorem. We have here that the product of rotation matrices, the tensor product of rotation matrices, and this is true for the matrix elements, so I don't have to actually, this is actually the product, those elements are that, is equal to that. So I have the following relationship here. It tells me that if I take YL1 M1 of theta and phi and multiply it by YL2 M2 of theta and phi, well, that's the product of two rotation matrix elements. And they're related this way. And I get the following relationship. This is equal to the square root of 2L1 plus 1 to L2 plus 1 over 4 pi. That Clebsch-Gordan series there, so I have these L prime sum with L prime M. L prime 0. L1, 0, L2, 0. O prime, M prime, L1, M1, L2, M2. Y, L prime, N prime of theta and phi. So, let me just conclude here and explain why we did all this mess. We've seen here this relationship between different irreps, taking products of them, and get sums of other irreps. We saw that with respect to the rotation operators. We saw that with respect to these kets, and we see that with respect to these spherical harmonics, which themselves were related to the kets and also rotation matrices. We made all these different, okay? Where we're headed with this is the following. So we're going to talk starting next week about the Wigner-Eckhart theorem. The Wigner-Eckhart theorem is a theorem that tells us about the tensor operators, and in particular, irreducible tensor operators. Okay? I'm going to explain what that means. But often, we're going to have things like dyadics, where we have products of things. And they themselves become sums of other irreducible operators. So this structure of reducible to irreducible is at the core of it all. And we're going to pick up on that next week. All right?